Welcome to Ready to Derive. In this video, we will explore the motion of a particle traveling along a straight line, known as rectilinear motion. While this may not sound like the most fascinating of topics, it's actually kind of fun, as you get to see the power of the derivative to answer interesting questions about real-world motion. So check this out. This is what we're looking at. So here's a line, a horizontal line. It could be vertical, it could be any line. And here's the particle kind of moving along to the right, stopping, turning back, and all the way back again, changing speed, sometimes at rest. Lots of interesting questions that we can answer. Just by knowing the function that describes the position of the particle along this line as a function of time, we will be able to answer questions such as when is the particle at rest? When is it moving left? When is it speeding up? And how far has it traveled over a particular time interval? Now that you are probably bristling with anticipation, let's get started. So let's begin with a scenario. A particle is traveling along the x-axis so that at time t is greater than or equal to 0, measured in seconds, its position is given by the following function. And in order to understand its motion, we are going to find x at various values of t, as shown in this table. And if you plug those values of t in, you will obtain these positions. And now we're going to try and sort of map out what it's doing on the x-axis. So we know the particle is starting at t equals 0, it's at x equals 2, which is right here. Sorry, let's get this right here. And 1 second later, it's at 7.5, so it seems to have been moving to the right in that direction. And then at t equals 2, it's at 4, which is back here. And you can see if you start to plot the motion of the particle along the x-axis, it's going to sort of get confusing as to where it's going when. So we have a technique to kind of draw out the trajectory a little more accurately. And what we do is we actually kind of elevate it and we say, okay, at t equals 0, let's pretend this is at position 2 on the x-axis. And this is where it is at t equals 1. Now at t equals 2, because it's backtracking, we are going to kind of elevate that slightly more. So that's t equals 2. So we know that it's coming along here. At t equals 1, or maybe just beyond it, it turns around and starts coming in the opposite direction. At t equals 3, it's at negative 2.5. So that's t equals 3. At t equals 4, it's at negative 6. So t equals 4. So it seems to be heading back. Again, we're not sure where it turns around. It could be somewhere between 4 and 5. So at t equals 5, it's at negative 0.5 here. And at t equals 6, wow, it looks like it's shot off to the right. So somewhere down here, along here, is going to be where t equals 6. So it seems like this is the motion. What we can't get precisely with the position function, though, is where the turnarounds occur. And some other details about the motion, which derivatives will help us to answer. So in the next slide, we're going to learn how the position and function relates to velocity and acceleration. So looking at the connection between position, velocity, and acceleration is where we get to have some fun with derivatives. So our position function was such from the slide before, and we know that by definition, velocity is, which I'm going to call v of t, is just the rate of change of position with time. Well, another way of writing that is x prime t. So we can just use the power rule and find that the position, the rate of change of position with time would be given by this function. And so I can figure out the velocity of this particle at any point in its motion. And similarly, acceleration is the rate at which velocity changes with time. So the instantaneous rate of change of velocity with time, so that's v prime t, which of course, if v is x prime, then v prime is just the second derivative of the position function. And applying the power rule again, we get 6t minus 15. And once again, for any particular value of time, I can find the particle's acceleration by just plugging in that value of t. So with these three functions in hand, there's a lot more depth we can analyze the motion of this particle with. So now that we have the velocity function, we can answer a very important question about the motion of the particle, like when is it at rest? So when is it temporarily not moving? That will matter because that will tell us when the particle potentially is stopped or turning around. So that will happen when its velocity is equal to 0. So we have the velocity function, and now we can set it equal to 0. And in this case, we can actually factor it. 5t plus 4 equals 0. And this factors as t minus 4, t minus 1, which means that at t equals 1 and t equals 4, the particle is at rest. So, and if this is on an AP exam, you would say the particle is at rest when t equals 1 and 4 seconds, and you have to give a reason. So you'd say because the velocity is 0 here. So now let's see how that helps us, more accurately map the trajectory of the particle. So here's the table from before, and notice that I've added in, I know the velocity is 0 at 1 and 4. And why does that matter? Because that is where, that pinpoints exactly where the particle is turning around. So I'm going to call up that number line again, and I'm going to put a more accurate graph of its motion. So I'm only interested now in kind of where it's turning around. Where it starts at t equals 0, it's at 2, and when and where it turns around. Now, so these particular points here, we weren't sure where this occurred before. Now we know the exact times at which it's temporarily stopped, and in this case, turning around. Bear in mind, when the velocity is 0, the object or particle doesn't necessarily have to turn around. It could have been stopped temporarily and then continue on in the same direction. Kind of like if you were driving a car and you came to a traffic light, you would stop, and then temporarily your velocity would be 0, and you'd start up and head in the same direction. So now that we know where the particle turns around, thanks to the velocity function, we can answer important question about the particle, the distance it travels over a certain period. And it's important to understand the difference between distance and displacement. So displacement's a little easier, so we'll start with that one. And we'll look over the interval 0 to 3. So the displacement is really just the net change in position of the particle over that time interval. So over the interval 0 to 3, let's see, it starts at x equals 2, so it starts here, and at 3 seconds, it's back here at negative 2.5. So the displacement ignores what happens in between those time intervals and just looks at where did it start, where did it end up, and how much of a change was that. So to work out displacement, you take the position at the end of the interval, so that's at 3 seconds, it's negative 2.5 it ended up at. You subtract where it started, so at 2. And so the displacement is negative 4.5, the negative indicating that the particle is now to the left of where it started. In contrast, the distance traveled over that interval can be broken into, well, has to be broken into 2 components, because it starts by traveling in what we will call the positive direction along the x-axis between t equals 0 and 1, and then it backtracks and continues on a little longer to here. So the distance has, to work out the distance, we need 2 components here, and that's given by these 2 expressions. Notice that I've put absolute value there because distance will have to be positive, and we want, unlike displacement, where the sign matters, for distance we're talking about positive quantity. So if we take these, let's see, x of 1, so at 1 second it's at 7.5, and at 0 seconds it was at 2, and the absolute value of 5.5 is just 5.5. So 5.5, it travels 5.5 units to the right, and then on the return journey, its position at 3 seconds is negative 2.5. At 1 second, it was 7.5, and that comes out to be negative 10 in there, and the absolute value of that is 10. So the total distance traveled is 15.5. So that journey in returning in this direction was 10 units. And that's the subtle but important distinction between distance and displacement. Now, another question we can answer using the velocity function is when is the particle moving left or right? We're just going to look at left in this case. Now, we kind of know that from before because we plotted the position function, but we don't even need to do that if we have the velocity function, because all we need to find out is when is the velocity negative. And for when is the particle moving right, it would be, of course, when the velocity is positive. So to do that, we first of all, once again, have to establish where is the velocity zero, because either it's positive, negative, or zero. So we take the zeros again of the velocity function, which we got before. And what we're going to do is we're going to analyze what's happening on either side of those values by using a number line. We're going to plot those zeros of VT on a number line. So here's our number line. And we have, let's see, so we know that time has to be greater than or equal to 0. And we know at time 1, its velocity is 0, and again at time 4. That means if those are truly the only zeros of velocity, that means that in between those values, 0 to 1, 1 to 4, and 4 and beyond, it can only be moving in one direction, right or left. Because if it changed directions, say between 1 and 4, if it changed directions, that means there would have to be another 0 of the velocity function in there, which there's not for this particular function. So so this sign chart, you've probably seen this before in pre-calculus, but we'll run through the steps. So what you have to do is you pick a test value of t in each interval. So let's see. Then we find the sign of VT at each of these values. So what do I mean by a test value? So a test value, we start by taking a value, say, in this interval between 0 and 1. So we could take a half. And we look at what would happen, what's the velocity going to be if we put a half in there. Now, we don't actually need the value of the velocity if it's not asked for. We just need to know the sign, as in SIGN. So a half take away 1, that would be actually negative. And a half take away 4 would also be negative. And a negative times a negative, with 3 there, of course, will be a positive. So we know that the velocity, I'm going to put a VT there to indicate that the sign refers to velocity, is positive between 0 and 1. And it can't ever be negative there, once again, because the particle only turns around or is stationary at 1 and 4. So let's take a value in here. So we could take 2, any value, and will work, and then it will be true for all values in that interval. So once again, the 3 sort of doesn't matter, but just in case you had factored out -3 of a function, it's good to keep that coefficient there. So 2 minus 1 will be positive, 2 minus 4 will be negative, the final answer will be negative. So the velocity remains negative between 1 and 4, and we remember that because the particle was moving in the reverse direction. And then one more value, so we have to take a value here, say we take 5, so we do 5 minus 1, 5 minus 4, and you can see that that actually comes out to a positive number also. So therefore we know where the particle, or when the particle is moving to the left. The particle is moving left on the interval 1 to 4 because that is where the velocity is negative. A common question about particle motion is to ask whether a particle is speeding up or slowing down in its motion. So we need to think about what is required for an object to speed up or slow down. And to help us think through this, I'd like to think of a person tossing a ball up in the air. So here's the ball, and as he tosses it up into the air, it moves up, up, and obviously slows down, right? Slows down. The green ball represents its maximum height. So why is it slowing down exactly? Well, we know it's because gravity is the acceleration due to gravity is pointing down towards the Earth, even though velocity, the velocity and the velocity as it moves up is positive. So if you think about it, the velocity is positive because that's the direction you're throwing it in, and the acceleration due to gravity in this case is negative because it's pointing towards the Earth. And because of that, because acceleration is counteracting velocity, that is the reason that the ball slows down. So if velocity and acceleration have opposite signs, an object will slow down. In contrast, on the way back down, what do we know happens to the ball? It's in the green position, the green ball, it's stationary, the velocity is 0. But as it heads down, it gets faster and faster, it speeds up. Now, why is that? Why is it speeding up on the way back? Well, acceleration hasn't changed. Actually, let's color code here. The acceleration hasn't changed. The acceleration due to gravity is still negative. But what has changed is that the velocity, the direction in which the ball is traveling, has changed. It is now, the velocity is now negative and the acceleration is negative, and put those two together and the object speeds up. So whenever the velocity and acceleration have the same sign, the object will speed up. So now we are equipped to answer the question, is the particle speeding up or slowing down at t equals 3? So let's recall the velocity function, the acceleration function, and then all we have to do is plug the value of 3 into each of them. So 3 in here will give -6 units per second. And then if we plug in 3 into the acceleration formula, the acceleration works out to be 3 units per second squared. The units being the measurement along the x-axis. It's just the generic unit. And because these are opposites, right? Because the acceleration and velocity are kind of counteracting each other, we know that the particle is slowing down at t equals 3, and there's the justification, because the velocity at 3 is less than 0 and the acceleration at 3 is greater than 0. So we will end by looking at a graph of the position function and a graph of the velocity function, and what we can determine by looking at a graph. So all these features are going to become very clear in a moment. So here is the position function. Remember, it was a cubic function, and that's a graph of it. And what we have to remember is that the derivative of the the position function is the velocity. And so if the derivative is the velocity, we can determine facts about that velocity based on the slope of this graph. So, for example, if we want to know when the particle is at rest, well, we know that that means that the velocity, that's where the velocity equals 0. But if velocity is slope, then we are looking for points where the slope is 0. So here at t equals 1, there's a max. Here at t equals 4, there's a min. So at t equals 1 and t equals 4 seconds, we know that the particle, we confirm that the particle is at rest. When is the particle moving to the right? Well, that will occur. We know that that means when the velocity is greater than 0. It will be moving to the right. Now, by the way, this graph, this position graph, this is not the graph of the trajectory of the particle. The particle is not moving along this graph. This is just a map or a record of the particle's position at any particular time. So moving to the right, we need the slope of the graph to be positive. Where is the slope of the graph positive? It looks like from here to 1, 0 to 1, and then from 4 onwards. So the particle is moving to the right, accordingly, from 0 to 1, and also 4 to infinity, assuming the particle never stops. So that's where the velocity, aka the slope of the graph, is positive. So when is the particle moving to the left? Well, that would be whenever the velocity is negative, aka whenever the slope of the position graph is negative, and that would occur from t equals 1 to t equals 4, as we discovered before using the sign chart. So interesting features that you can answer just given the position graph and knowing that the velocity at any point represents the slope of the position graph. So in this last example, we look at the graph of the velocity function and see if we can answer all these questions based on just the graph. So that's the function. It was a quadratic, and the graph is a parabola. And so you can answer things like, when is the particle at rest? Because we know that when the particle is at rest, we know that v of t equals 0. But since we've actually got the graph of the velocity, we are just looking for the x-intercepts. So the x-intercepts are where the graph is equal to 0, is where the velocity is equal to 0. And once again, we know that that's at t equals 1 and 4. What about when is the particle moving to the left? Well, it's moving to the left, we know, when vt is less than 0. And here you have to just sort of think about the graph overall. When is the velocity function less than 0? It's basically less than 0 when it's below the x-axis. So the portion of the graph that's below the x-axis is between 1 and 4. And that leaves, in terms of moving right, that would be wherever v of t is greater than 0, which means we're looking for the function being above the x-axis. This is the velocity is greater than 0. And so that's, again, from 0 to 1 and 4 to infinity. But we get a little more out of this graph as well. So we actually, since this is the velocity graph and we know that acceleration is the derivative of velocity, we know that the slope at any point of this graph reveals the acceleration. So now we can determine, for example, when is the particle slowing down versus when is the particle speeding up. And maybe it might be good to sort of take an overall picture of this, a look at this. So we can see that the velocity here, the initial velocity of the particle is 12. And we know that over this interval, the velocity goes from 12 to 0. So we have a feeling that this must indicate that the particle is slowing down. And why? I mean, what does that have to do with what we learned before about acceleration and velocity? Well, notice that since velocity is above the x-axis, the function above the x-axis, the velocity is positive. But because the function is decreasing, the slope, aka the acceleration, is less than 0. And since they're in opposite directions, we know that the particle is going to be slowing down. So that we know from 0 to 1 that is slowing down. Now, where else might we have this situation going on? Well, let's look down here. Down here, the velocity is pretty negative, but it's like nearly negative 7. And then it's heading back down to 0. So once again, it's slowing down. But what's different here? Different here is that the velocity is negative because it's below the x-axis, and the acceleration is positive. Once again, they're operating in opposition to one another. So therefore, that looks like about 2.5 to 4. Well, that leaves the other intervals for speeding up, but let's understand why. So let's see here, the velocity is going from 0 to nearly negative 7. We have, and so therefore it's obviously speeding up in a negative direction. We have velocity is negative, and the slope of this function here is also in this interval, is also negative, so the acceleration is negative. They match, and therefore from 1 to 2.5, it's speeding up. And let's have a look at what's remaining here. Right over this portion, we know that the velocity is positive because it's above the x-axis, the function, and the slope, because the function's increasing, we know that the slope, aka acceleration, is also positive. So from 4 to infinity, we know it's speeding up. So just like to end by summarizing everything that's been thrown at you regarding particle motion, because it's quite a lot. The displacement of a particle over AB is given by the position at time B minus the position at time A. When is the particle at rest? When the velocity equals 0. What is the distance traveled over that interval AB? Well, this is a little more cumbersome, so I'll take a couple of examples. Let's say that the particle is only at rest one time at t1. Then we have to divide the distance calculations into basically two displacement ones. So we sort of consider what happens, say, from t equals A to t equals t1. We find that distance, and then we find the distance from t1 to B. Now, that's if it only sort of is stationary or, at rest once. What if it was at rest at a second time, t2? And so to take that into account, we would have to divide up the calculation into three parts. Say T2 happened to be right here. So now it could be that it doesn't turn around at t equals t2. So technically, did you have to break it up like that? Not necessarily, but just to be safe, you might as well break it up into the 3 components. Okay, when is it moving forwards or backwards? Well, obviously velocity is greater than 0 for forwards. Now forwards means either to the right if you're on the x-axis, or upwards if you're on the y-axis, if this particle is traveling on the y-axis. And backwards is the velocity is less than 0. When is the particle speeding up? When v and a have the same sign. And when is a particle slowing down? When the velocity and acceleration have opposite signs. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.